I love space. It's so interesting and mysterious and cosmic and huge, so let's cover an iceberg about it. This one's been requested a lot, and after the Ocean Mysteries Iceberg, I thought it's finally time for me to do this. Let me know in the comments what you want to see next. Be sure to follow my Instagram, join the Discord, we can hang out, and most importantly, subscribe to the channel. I want to reach 500k by the end of the year. We might not be able to do it, but it'll make me so happy if we do, guys. Okay, straight into the iceberg, starting in layer 1 with space has no sound. Sound waves need a medium like air or water to travel, and space is almost a perfect vacuum. That means there aren't enough particles bumping into each other to carry the vibrations we perceive as sound. Astronauts outside the ISS, for example, wouldn't hear an explosion happening a few feet away. That said, certain regions of space, like dense gas clouds or plasma fields, can carry pressure waves that scientists translate into sound. NASA has even sonified data from black holes and nebulae, not because you'd hear it in space, but because the frequencies could be shifted into audible ranges. And also, before we get too far, I'm just gonna go ahead and mention now, just for those who don't know, an iceberg works by, we're gonna cover the pretty basic stuff in the first few entries, the more boring stuff that most people know about. And then we're gonna get into the more disturbing and mysterious stuff as we go on, so stay tuned. Pluto is just a planet. Pluto was discovered in 1930 by Clyde Tombaugh, hailed as the 9th planet of the solar system. For decades, it held that title despite being smaller than Earth's moon. But in the 1990s and 2000s, astronomers began finding other objects in the Kuiper belt, some nearly as large as Pluto, like Eris. This forced the International Astronomical Union, or IAU, in 2006 to define what a planet actually is. Their definition required that an object A orbits the sun, B is spherical, and C has, quote, cleared its orbit of other debris. Pluto fails that last test, so it was reclassified to a dwarf planet. The backlash was huge. To the public, Pluto had always been the underdog planet, small, far away, and beloved in textbooks and pop culture. Scientists like Alan Stern, who led NASA's New Horizons mission, argue that the IAU's definition is flawed and too Earth-centric. They point out that Pluto is geologically active, has an atmosphere, and should count as a planet in its own right. The debate continues even today. For many people, saying Pluto is a planet is more of an emotional stance than a scientific one. The sun will die someday. Our sun is about 4.6 billion years old, roughly halfway through its life cycle. It steadily fuses hydrogen into helium, but eventually that hydrogen will run out. In about 5 billion years, the sun will swell into a red giant, engulfing Mercury and Venus, and maybe even Earth. After that phase, it will shed its outer layers into a planetary nebula, leaving behind a dense white dwarf that will cool for trillions of years. The mystery isn't whether this will happen, but exactly how violent Earth's end will be. Some models suggest our planet might be consumed by the sun, while others say it'll just be roasted into an uninhabitable husk. Either way, humanity won't be around to see it unless we've long since left the solar system. Exoplanets. For most of history, no one knew if planets existed beyond our solar system. That changed in 1992 when astronomers Alexander Volkskin and Dale Frail discovered planets orbiting a pulsar. Then in 1995, Michael Mayer and Didier Queloz confirmed the first planet orbiting a sun-like star, 51 Pegasi b. Since then, technology like the Kepler Space Telescope has revealed thousands of exoplanets across the galaxy. These discoveries shattered our old assumptions. Many exoplanets don't look anything like our neat solar system. There are hot Jupiters orbiting scorchingly close to their stars, super-Earths bigger than our own planet but smaller than Neptune, and even worlds that may be covered entirely in oceans. The sheer diversity suggests that planetary formation is far more chaotic than we once thought. The search for exoplanets is closely tied to the hunt for life. Astronomers look for planets in the habitable zone where liquid water could exist. A handful of promising candidates like Proxima Centauri b or the TRAPPIST-1 system have fueled speculation that Earth-like worlds may not be rare. What makes exoplanets mysterious is not just that they exist, but that we can only study them indirectly. Most are too far away to image directly, so astronomers infer their presence from wobbles in a star's light or tiny dips in brightness as a planet passes in front. Every discovery hints at an unseen landscape that, for now, is hidden from us. Black holes. Black holes are one of the most extreme objects in the universe. They form when massive stars collapse under their own gravity, compressing all their matter into a singularity, a point of infinite density. Surrounding that is the event horizon, the boundary beyond which not even light can escape. The very idea breaks common sense. Space and time themselves are warped so drastically that the laws of physics seem to bend. They were predicted by Einstein's general relativity in 1915, but for decades they were treated as mathematical oddities rather than real objects. In the late 20th century, evidence began piling up. Stars orbiting invisible companions, X-rays streaming from matter being devoured, and eventually the Event Horizon Telescope's 2019 image of the black hole in galaxy M87. The mystery isn't just their existence, but what happens inside them. The singularity defies known physics. Quantum mechanics and relativity don't agree there. Do black holes destroy information, or is it preserved somehow, as Stephen Hawking once debated? The information paradox remains one of the biggest open questions in science. Black holes also aren't just endpoints, they shape galaxies. Supermassive black holes, millions to billions of times the mass of the sun, sit at galactic centers and seem to regulate star formulation with their energy jets. Their sheer scale raises another question. How did they grow so fast in the early universe? Even stranger, black holes might not be permanent. Hawking radiation suggests they can slowly evaporate over unimaginable timescales. If true, the universe's future could not end with fiery explosions, but with black holes quietly fading into nothingness. Age of the universe. Figuring out how old the universe is has been one of cosmology's central puzzles. Using the expansion of galaxies discovered by Edwin Hubble, scientists realized the universe had a beginning, the Big Bang. Measuring the rate of expansion, the Hubble constant, and comparing it to the cosmic microwave background, researchers have estimated the age at about 13.8 billion years. But even here, there's controversy. Different methods of measuring expansion give slightly different numbers, a problem known as the Hubble tension. Some studies suggest 13 billion years, others over 14. The disagreement could mean our models are missing something, perhaps new physics or unknown particles affecting cosmic evolution. This uncertainty is why the age of the universe remains not just a number but a mystery. It's the foundation for every other timeline in astronomy, yet the exact figure is still debated by some of the brightest minds in the field. Center of the galaxy. Astronomers have found that nearly every large galaxy harbors a supermassive black hole at its center. The Milky Way's is called Sagittarius A, weighing about 4 million suns. Some galaxies host black holes billions of times larger. These central giants likely grew from smaller black holes formed early in cosmic history, feeding on gas, stars, and even merging with each other. The relationship between galaxies and their central black holes is still mysterious. Black hole activity can power quasars and active galactic nuclei, pouring out more energy than entire galaxies. Yet they also seem to regulate star formation. This feedback loop suggests that galaxies and their central black holes co-evolve, but the details of how that happens remains unclear. Laika was a stray dog from Moscow who became the first living creature to orbit Earth. In 1957, the Soviet Union launched her aboard Sputnik 2, a mission rushed to coincide with the 40th anniversary of the Russian Revolution. The spacecraft wasn't designed for recovery, meaning that Laika was never meant to return. Soviet officials initially claimed she lived for several days, but later reports revealed she likely died within hours from overheating and stress. The mission was controversial from the start, criticized as inhumane, but it also captured global attention. Laika became both a symbol of scientific progress and a tragic reminder of its costs. Today, Laika is remembered with statues and memorials in Russia. Her story marks an important moment in the space race, highlighting the sacrifices made, both human and animal, to push the boundaries of exploration. And with that, guys, that is the end of layer 1. I kind of just got some pretty basic ones just to get us into it, and now we're gonna get into the next layers, layer 2, the tyranny of the rocket equation. So Tsiolkovsky first laid out the math of space travel in 1903, in what has become known as the rocket equation. It's simple at first. The velocity that a rocket can reach depends on the exhaust speed of its fuel and the ratio between its total starting mass and its final mass after the fuel burns off. But the deeper you look, the more depressing it becomes. Add more fuel and the rocket gets heavier, which means you need more fuel just to move that extra weight. The cycle feeds in itself until you realize most rockets are basically giant flying gas tanks with a tiny payload on top. That's why people call it the tyranny. The math itself rules over what's possible. Staging rockets was the hack that we developed to deal with this. You throw away the empty tanks to get lighter mid-flight. Without staging, missions like Apollo 11 could never have even left Earth. Even today, launch vehicles like the Falcon 9 or SLS are fundamentally fighting against the same curve. The equation also explains why interstellar travel is so daunting. Chemical rockets can get us to the moon or even Mars with difficulty, but anything beyond that starts to break under the tyranny. To really break free, engineers look to nuclear propulsion, solar sails, or exotic concepts like antimatter drives. Until then, every launch is just a reminder of how limiting basic physics can be. Next entry is historic supernovae. In ancient records, sudden new stars would appear in the night sky, sometimes bright enough to be seen in daylight. These were supernovae, though observers didn't know it at the time. The Chinese recorded one in 185 AD, considered the oldest confirmed supernova. But the most famous historic case came in 1054, when a star exploded so brightly it was visible during the day for nearly a month. Today, we know that event produced the Crab Nebula, still glowing with its pulsar at the center. European astronomers also contributed to the record centuries later. Tycho Brahe described the new star of 1572 in detail, and his observations helped overturn the Aristotelian belief that the heavens were unchanging. Kepler's supernova in 1604 reinforced the point. Stars could die and the universe was dynamic. These events reshaped not just astronomy but philosophy, since the cosmos was no longer thought of as eternal and perfect. Modern science has been able to match up these written accounts with physical remnants in space. The Crab Nebula's expanding filaments line up almost exactly with the timing of 1054. Other remnants like Cassiopeia A point to supernovae that either weren't well recorded or were missed entirely. The mystery that lingers is not whether these explosions happened, but why they occur in slightly different ways. Some stars collapse into black holes, others leave neutron stars, and some fizzle as failed supernovae. Even now, astrophysicists can't predict with certainty which massive stars will go out in a blaze versus which will just collapse quietly. Stellar classification. When astronomers started cataloging stars by their light, they noticed patterns in the absorption lines of their spectra. This led to the Harvard classification system, O, B, A, F, G, K, M, from the hottest blue-white giants down to the coolest red dwarfs. It looks random, but it's based on how the early system was reorganized once scientists realized temperature, not hydrogen content, was the key factor. Our sun, for example, is a G-rated star. The classification unlocked a huge mystery: why stars look different colors, live for different times, and die in different ways. It gave us the Hertzsprung-Russell diagram, which basically maps out stellar evolution from birth in a nebula to death as a white dwarf, neutron star, or black hole. TV static. Back when TVs used analog signals, if you turned to a dead channel, you'd see that fuzz of black and white snow. A tiny percentage of that static, about 1%, actually came from space. Specifically, it was the cosmic microwave background radiation, the afterglow of the Big Bang itself, still echoing across the universe. The fact that everyday living rooms unknowingly contained traces of the universe's origin is one of the coolest space facts. Two radio astronomers, Penzias and Wilson, discovered the CMB in the 1960s while investigating what they thought was interference in their antenna. That radiation is now one of the most important clues we have about the early universe, mapping how matter clumped together to form galaxies in the first place. Cosmic rays. Cosmic rays are high-energy particles, mostly protons, that slam into Earth from outer space at near light speeds. When they hit the atmosphere, they create showers of secondary particles that rain down on the surface. Some even pass through our bodies every second without us noticing. They were first detected in the early early 1900s by balloon experiments, proving that radiation was coming from space and not just the Earth itself. The real mystery lies in where the most energetic cosmic rays come from. Some clearly originate from supernovae, while others may be accelerated by black holes or neutron stars. But the highest energy rays, so powerful they make our biggest particle accelerators look weak, don't match up neatly with known sources. Astronomers still debate whether they're products of distant galaxies, gamma ray bursts, or something even stranger. Cosmic rays also pose a practical problem for space travel. They can damage spacecraft electronics, mutate DNA, and increase cancer risks for astronauts. Shielding against them is not easy since their energy allows them to penetrate most materials. Solving the mystery of their origins might also help us solve how to survive them. Micrometeorites. Earth is constantly bombarded by tiny fragments of rock and metal from space. Micrometeorites. Unlike the big, rare meteorites that make headlines, these are microscopic to millimeter-sized particles, billions of which fall to Earth every day. They mostly burn up in the atmosphere, but some survive and settle in places like Antarctica or the ocean floor. What makes them interesting is the information they carry. Micrometeorites are basically samples of the solar system delivered free of charge, preserving materials from asteroids, comets, and even interstellar dust. Studying them gives scientists clues about how planets formed and what chemical ingredients were present in the early solar system. For astronauts, though, micrometeorites are a hazard, traveling at tens of thousands of miles per hour. Even a grain-sized particle can puncture a spacesuit or a spacecraft wall. The Kuiper Belt. Beyond Neptune lies the Kuiper Belt, a vast ring of icy bodies extending about 30 to 55 astronomical units from the Sun. It's like a second asteroid belt, but far colder and larger, holding remnants from the solar system's formation. Pluto, Haumea, and Makemake are some of its most famous residents, and many smaller objects are still being discovered. Also, am I pronouncing the Kuiper Belt correctly? Oh, Kuiper. My fault, okay. The Kuiper Belt reshaped our understanding of the solar system. When astronomers found Eris in 2005, nearly the same size as Pluto, it forced the planet definition debate that ended with Pluto's demotion. It also showed that the outer solar system is far more populated than we once thought, with potentially hundreds of thousands of small icy worlds. But mysteries remain. The orbits of some Kuiper Belt objects appear oddly aligned, which has led to some speculation about an unseen Planet 9 lurking even further out. Whether that's real or not, the Kuiper Belt is one of the keys to understanding how the solar system formed and how its architecture evolved. The Oort cloud. Even farther out, at the edge of the sun's gravitational reach, is the hypothetical Oort cloud. Unlike the Kuiper Belt, no one has ever directly observed it, but astronomers infer its existence because long-period comets, ones that take thousands of years to orbit the sun, seem to come from a distant spherical reservoir of icy bodies. The Oort cloud is thought to extend from around 2,000 astronomical units to possibly 100,000, making it a light year away in some directions. That is so far that passing stars or galactic tides could disturb its objects, sending them plunging toward the inner solar system as comets. Every great comet you see in the night sky may be a messenger from this invisible frontier. Its origins are still debated. One theory is that these icy bodies formed closer to the sun and were flung outward by the gravity of the giant planets billions of years ago. Another idea is that some might even be captured debris from other star systems, meaning the Oort cloud could be a mix of both local and alien material. The Oort cloud represents the true outer boundary of the solar system, if it exists as predicted, but because it's so distant and dark, confirming it directly may not happen for decades, leaving it one of astronomy's most haunting mysteries. Antimatter. Antimatter is one of the strangest concepts in physics. For every particle, there is a mirror opposite, the positron for the electron, the antiproton for the proton. When matter and antimatter meet, they annihilate in a burst of pure energy. Scientists can create antimatter in particle accelerators and is even used medically in PET scans. But here's the catch. The observable universe is almost entirely made of matter. According to the Big Bang, matter and antimatter should have been created in equal amounts. If that were true, they should have canceled each other out, leaving only radiation behind. Yet, clearly we exist in a universe full of matter. Why? The imbalance happened is one of the biggest unsolved mysteries in cosmology. Some theories suggest subtle asymmetries in particle interactions gave matter a tiny edge in survival. Others point to physics beyond the standard model that haven't been discovered yet. Antimatter also has practical importance. It shows up naturally in cosmic rays and near black holes, and scientists can produce tiny amounts of it in labs like CERN. But storing it is nearly impossible. It annihilates the instant it touches normal matter, so it has to be trapped in magnetic fields. That makes it incredibly expensive. Producing just a milligram would cost billions of dollars. Science fiction often imagines antimatter as the ultimate fuel source, a perfect conversion of mass into energy far beyond chemical or even nuclear reactions. In theory, a gram of antimatter could power a spacecraft to Mars, but in reality, we are nowhere near close to generating or storing it in any kind of useful quantity. And the mystery of why the universe favors matter over antimatter reserves unanswered. And if we ever crack it, it won't just explain why we're here. It might open doors to entirely new physics. Bird legs, puffy face. This odd phrase refers to the physical effects of microgravity on astronauts. In space, without Earth's gravity pulling fluids downward, blood and other bodily fluids shift towards the upper body. The result is a puffy face from fluid swelling and bird legs from thin, weakened lower limbs that aren't bearing weight. Astronauts often report feeling congested and their calves shrink in muscle mass over time. It sounds funny, but really it's a serious issue. Long missions in space mean muscle atrophy, bone density loss, and cardiovascular changes. NASA combats this with exercise regimens and resistance machines aboard the ISS, but the bird legs puffy face look is one of the most visual reminders of how different and dangerous living in zero-G can be. It also raises the big what if. How can humans realistically adapt to long voyages to Mars or beyond if our bodies are literally reshaped by space? Cornered beef sandwich. This comes from a small but infamous space history joke. In 1965, astronaut John Young smuggled a cornered beef sandwich aboard Gemini 3 as a joke for his crewmate Gus Grissom. Once in orbit, he pulled it out and took a bite, but the bread immediately started shedding crumbs. In zero-G, loose particles can float into electronics, air filters, or astronauts' eyes, creating a serious hazard. Mission Control was not amused. Congress even brought it up in a hearing, concerned that food safety in space wasn't being taken seriously. NASA responded by focusing on safer, crumb-free space foods. Tortillas eventually replaced bread on shuttles in the ISS. What seemed like a harmless prank actually highlighted how even small details like the texture of food can become life-threatening in space. The mystery angle here is less cosmic and more human. It shows how unpredictable behavior and small oversights can ripple out in the high-stakes environment of spaceflight. A single sandwich nearly derailed NASA's reputation for precision, a reminder that sometimes the biggest risks come from the smallest things. Fusion. Fusion is the process that powers stars. Atoms of hydrogen fusing into helium under extreme heat and pressure, releasing vast amounts of energy. Unlike nuclear fission, which splits heavy atoms apart, fusion combines light atoms and it produces little radioactive waste. If harnessed on Earth, it could be the ultimate energy source. Clean, abundant, and nearly limitless. The sun makes it look effortless, but replicating fusion in a lab is brutally difficult. Temperatures need to be hotter than the sun's core because we don't have the crushing power of stellar gravity. Tokamak stellarators and laser-driven experiments have been pushing the boundaries for decades, chasing the point where the reaction produces more energy than it consumes, ignition. In 2022, researchers at the National Ignition Facility briefly achieved that milestone, but scaling it up is a whole other challenge. For space exploration, fusion is the holy grail of propulsion. A fusion-powered spacecraft could reach the outer planets in months instead of years, and potentially cross to nearby stars within human lifetimes. Concepts like the British Daedalus project in the 1970s imagined enormous fusion ships that could travel interstellar distances. The mystery is less about whether fusion works, because we know it does, and more about whether humanity will ever tame it outside of stars. And if we do, it could solve both Earth's energy crisis and unlock a new era of space colonization. The Fermi paradox. Enrico Fermi famously asked in 1950, "Where is everybody?" Given the vastness of the universe with billions of galaxies, each holding billions of stars and likely countless planets, intelligent life should be common. yet we see no clear signs of it. This contradiction is the Fermi paradox. One explanation is that intelligent life is rare. Maybe the conditions that produced Earth are freakishly unlikely. Another is the Great Filter hypothesis. At some stage in evolution, most civilizations fail, whether at the jump from microbes to complex life, from intelligence to technology, or from technology to survival without self-destruction. If the filter lies ahead of us, humanity may be doomed to the same fate. Other ideas are less grim, but equally fascinating. Civilizations may exist but choose not to broadcast, hiding in a galactic zoo. Or they may communicate in ways we don't recognize, through neutrinos, dark matter, or dimensions beyond our perception. Some suggest we may be looking too late. Alien civilizations could rise and fall on timescales of millions of years, barely overlapping with ours. A more unsettling angle is the possibility that advanced life is out there, but deliberately avoiding us, or that we're already surrounded by signs we don't recognize. The so-called dark forest theory from science fiction suggests that civilizations stay silent out of fear, because broadcasting your presence in a universe full of unknowns is a death sentence. The Fermi paradox is one of the most haunting mysteries in space science. It blends numbers, probability, and imagination into a question with no answer. If life should be everywhere, why does it feel like we're alone? And guys, that was Layer 2. So if you're still here, thanks for watching. Make sure you got some water, a snack or something, stay hydrated. And let's get into Layer 3. Interstellar journey times. The nearest star system, Alpha Centauri, is about 4.3 light years away. At current technology levels, that distance might as well be infinite. Voyager 1, our farthest spacecraft, is moving at 17 kilometers per second and has taken nearly 50 years just to cross into interstellar space. But even at that speed, it would need over 70,000 years to reach Alpha Centauri. The math is brutal. Even future upgrades like the nuclear propulsion we were talking about could only shave that down to thousands of years. Theoretical fusion engines like the British Interplanetary Society's 1970s Project Daedalus could cut the trip to a few centuries. More exotic concepts like antimatter drives, solar sails powered by giant lasers, or even warp drives could bring the time down to decades or less, but it all remains speculative. The mystery here isn't whether it's possible, but when and by what means. If humanity ever leaves the solar system, it will mean confronting the same cold equations that limit rockets today, but stretched across cosmic distances. In one secret moon rocket, during the 1960s, while the US was developing the Saturn V, the Soviet Union secretly built its own giant rocket to send cosmonauts to the moon, the N1. It was enormous, taller than the Statue of Liberty, with 30 engines clustered in its first stage, but it was plagued by technical problems. Between 1969 and 1972, the N1 launched 4 times, and every attempt failed spectacularly. The second test in 1969 resulted in one of the largest non-nuclear explosions in history. Because the Soviet lunar program was classified, the world didn't learn the full story until the 1990s. The failures were covered up while the US Apollo program played out on TV. The mystery angle here is that for decades, people just assumed the USSR never seriously tried to land on the moon. And in reality, they had. Their failures were just hidden. Lost cosmonauts conspiracy theory. The lost cosmonauts theory claims that the Soviet Union may have launched humans into space before Yuri Gagarin's official 1961 flight, and that some of those missions ended in death quietly covered up. The idea gained traction in the early 1960s when Italian brothers Achille and Giovanni, amateur radio operators, said they intercepted transmissions of dying cosmonauts calling for help. These recordings included alleged heartbeats and garbled voices fading into static. Soviet secrecy during the Cold War fueled this suspicion. Official documents were tightly controlled, and the USSR had a history of covering up disasters. Skeptics pointed out gaps in early launch records and inconsistencies in official timelines. Stories circulated about cosmonauts who supposedly disappeared from photographs or whose missions were erased from history. But most historians and space experts today consider the theory very unproven. Many of those tapes were seen as hoaxes or misinterpretations. At least today they are. The technical timeline of rocket development also makes some of the claims unlikely, especially the supposed manned launches in the late 1950s, before even uncrewed tests had succeeded. Still, the conspiracy lingers because it captures a pretty haunting idea, that before the triumphs of things like Gagarin, Sputnik, and Luna, there may have been unacknowledged sacrifices lost in the void. Government cover-ups are always like creepy, dude, for some reason, I don't know. Dark matter. In the 1930s, Swiss astronomer Fritz Zwicky studied galaxy clusters and noticed something strange. The galaxies were moving too fast to be held together by the visible matter alone. Later, in the 1970s, Vera Rubin confirmed the effect in spiral galaxies. Their outer stars orbited far faster than Newtonian physics predicted. The only explanation was that some unseen mass was exerting gravitational pull. That invisible material became known as dark matter. Today, dark matter is thought to make up about 27% of the universe, compared to just 5% for ordinary matter. It doesn't emit, absorb, or reflect light, making it completely invisible. We only know it's there because of its gravitational influence on galaxies and the cosmic web. The mystery is like what it actually is. Leading candidates are WIMPs, or weakly interacting massive particles, or axions. But decades of experiments, from underground detectors to particle accelerators, have yet to find a single confirmed particle. Some scientists propose alternatives like modifying gravity itself, which is the MOND theory, rather than invoking new matter. Dark matter also shapes the large-scale structure of the universe. Computer simulations show that galaxies form and cluster in halos of dark matter, as if the invisible scaffolding guides the visible cosmos. Without it, the universe we see today just couldn't exist. Moon dust is dangerous. When Apollo astronauts returned from the moon, one of their biggest complaints wasn't about low gravity or bulky suits, it was the dust. Lunar regolith is made of jagged, glassy particles created by micrometeorite impacts over billions of years. Unlike Earth sand, it hasn't been smoothed by wind or water, so it's razor sharp at the microscopic level. It clung to everything: suits, instruments, and even the astronauts' lungs. Harrison Schmitt of Apollo 17 described lunar hay fever from inhaling the dust, and engineers worried about its potential long-term health effects. On equipment, it was abrasive enough to wear down seals, scratch visors, and clog joints. NASA later concluded that lunar dust would be one of the biggest hazards for any long-term moon base. Diamond planets. Astronomers have theorized that some exoplanets could be composed largely of carbon. Under high pressure, that carbon could crystallize into diamond. One candidate is 55 Cancri E, a super-Earth about 40 light-years away. Some early models suggested its interior might be diamond-rich, though later studies have been less certain. Whether or not whole diamond planets exist, carbon-rich worlds would look radically different from Earth. Instead of blue oceans and silicate crusts, they might have graphite or diamond landscapes and hydrocarbon atmospheres. And this idea kind of highlights how diverse planetary chemistry can be once you look beyond our solar system. Solar sails. A solar sail is a spacecraft that moves using the pressure of photons, or light particles, from the sun. Though photons have no mass, they carry momentum, and over time, that pressure can accelerate a reflective sail. Unlike rockets, solar sails don't need fuel, meaning they could, in theory, keep accelerating as long as sunlight or laser light hits them. Japan's Ikaros mission in 2010 successfully tested a solar sail in interplanetary space, and the Planetary Society's Light Sail project demonstrated controlled solar sailing in Earth orbit in 2019. These small missions prove the physics actually works. The real promise is in deep space travel. Concepts like the Breakthrough Starshot propose using powerful Earth-based lasers to push tiny solar sails to 20% the speed of light, reaching Alpha Centauri in a couple decades. It's one of the propulsion ideas that scales to interstellar distances without impossible amounts of fuel. The flags on the moon are now white. Between 1969 and 1972, Apollo astronauts planted 6 US flags on the moon. Photos from later lunar missions and satellite satellite imagery suggests most of them are still standing. However, decades of unfiltered solar radiation have bleached the nylon fabric. So yeah, now they're white. Acceleration and gravity equivalence. Einstein's equivalence principle says that being in a sealed room experiencing acceleration feels the same as being in gravity. So if your spaceship accelerates upward at 9.8 meters a second squared, you'd feel the same weight as you do standing on Earth. This simple thought experiment was a cornerstone of general relativity because it linked gravity and acceleration as two sides of the same thing, the warping of spacetime. And it's not just theory either. This is why astronauts in orbit feel weightless. They're not outside of Earth's gravity, they're in free fall, constantly accelerating toward the planet while moving fast enough sideways to miss it. Principle also shapes how we imagine artificial gravity in space travel. Not with gravity generators, but with spinning habitats and steady acceleration. Titan lakes. Saturn's largest moon, Titan, is the only place in the solar system besides Earth with stable liquid on its surface. But instead of water, Titan's lakes, rivers, and seas are filled with liquid methane and ethane, thanks to its extremely cold temperature of negative 290 degrees Fahrenheit. NASA's Cassini mission mapped these lakes, especially the huge seas near the North Pole, like Kraken Mare and Ligeia Mare. The chemistry there is alien. Titan has a thick nitrogen atmosphere with methane rain, producing an entire methane cycle similar to Earth's water cycle. Some lakes are hundreds of feet deep, and radar data suggests that waves might ripple across them. Scientists are even planning a submarine-style probe to one day explore Kraken Mare, which is the name of that one sea. The mystery is whether Titan could host life. It wouldn't be water-based life like ours, but some researchers speculate methane could support exotic chemical alternatives. At the very least, Titan offers a glimpse of what strange versions of habitability might look like elsewhere in the universe. Cosmic inflation. The Big Bang explains the early expansion of the universe, but in the 1980s, physicists realized that there was a deeper puzzle. The universe looks remarkably uniform in every direction. The cosmic microwave background has nearly the same temperature everywhere. That shouldn't be possible unless those regions were once in contact. The solution proposed was cosmic inflation, a split-second period right after the Big Bang when the universe expanded exponentially faster than light. Inflation explains why the universe is so flat and even and why galaxies formed in the way that they did. Tiny quantum fluctuations during inflation would have been stretched out into the seeds of cosmic structure we see today. It ties the physics of the very small to the largest scale imaginable. But inflation is not fully proven. The smoking gun would be a certain type of polarization pattern in the cosmic microwave background, which scientists have been hunting for. In 2014, one experiment thought they had found it, but it turned out to just be dust in our own galaxy. So inflation remains the leading theory, but with open questions. What exactly triggered it? What field or particle drove it? And did it ever truly stop, or does it imply that other universes, parts of a larger multiverse, inflated beyond our reach? Apollo 1. Apollo 1 was meant to be the first crewed Apollo mission, but it ended in tragedy. On January 27, 1967, astronauts Gus Grissom, Ed White, and Roger Chaffee were conducting a ground test when a fire broke out inside their capsule. Because the cabin was pressurized with pure oxygen, the flames spread almost instantly. The crew couldn't escape. The hatch was designed to open inward and was sealed by the pressure. All three died within minutes. The investigation revealed serious design flaws: flammable materials in the cabin, poor wiring, and the unsafe oxygen environment. NASA overhauled the spacecraft after the disaster, redesigning the hatch to open outward in seconds and using safer materials. The tragedy reshaped the Apollo's program safety culture. And though devastating, Apollo 1 ultimately prevented future accidents by forcing those changes. The very fact that Apollo 11 could land safely 2 years later was in part because of the lessons learned from this fire. So at least some good came out of it, even though it's really sad. Mirror incidents. The Soviet, later Russian, space station Mir operated from 1986 to 2001 and was a pioneering outpost, but it also had a reputation for near disaster. In 1997, a supply ship called Progress collided with Mir during a manual docking test, puncturing a module and causing it to depressurize. The crew had to scramble to seal the hatch and shut down power, working in near darkness to save the station. There were also frequent technical problems, power failures, computer crashes, and even a major onboard fire that filled the station with toxic smoke. The fire was from a malfunctioning oxygen generator, and the crew had to put it out with extinguishers while wearing respirators. Some accounts describe how terrifyingly close they came to losing control. Despite the chaos, Mir stayed in service for 15 years, hosting international astronauts and scientific experiments. It became a proving ground for long-term spaceflight, even if conditions were far harsher than on the ISS today. These incidents highlighted both the resilience of the cosmonauts and the risks of cutting-edge space engineering. Mir was often patched together and repaired in orbit, more like a survival project than a polished laboratory. The WOW signal. On August 15th, 1977, Jerry Emman was working with Ohio State's Big Ear radio telescope when he recorded a sharp 72-second spike in radio intensity. It stood out so clearly from the background that he circled it on the printout and wrote "WOW" in red ink. The signal came from the constellation Sagittarius near the galactic center and matched what you'd expect from a narrowband radio transmission, something nature rarely produces. The WOW signal became one of the most famous potential pieces of evidence for extraterrestrial intelligence. Unlike random noise or satellites, it fit the profile of a deliberate transmission, but follow-up observations never detected it again. Despite years of searching the same region, the signal never repeated. Explanations have ranged from comets releasing hydrogen clouds, a more recent suggestion, to military satellites to genuine alien broadcasts. None have been confirmed. The signal's exact origin remains unsolved because it was too short and it never returned. What makes it stand out is how perfectly it matched what SETI or SETI researchers were looking at, a strong, clean, narrow-band signal from space. But science demands repeatability, and the WOW signal remains a one-off. Nearly 50 years later, it still sits in that uncanny category. Not proven alien contact, not fully explained natural phenomenon, just a single unexplained blip in the noise of the universe. And that's the end of Layer 3. So let's get into Layer 4, guys. Hell yeah, man, let's do this. Make sure you still got your water, bruh. Vladimir Komarov's sacrifice. Vladimir Komarov was a Soviet cosmonaut and close friend of Yuri Gagarin. In 1967, he was assigned to fly Soyuz 1, the first mission of a new spacecraft design. Engineers already knew the craft had major flaws. Hundreds of technical issues were logged before launch. But the political pressure of the 50th anniversary of the October Revolution meant it went forward anyway. Komarov knew the risks. Accounts suggest he told colleagues he expected to die, but insisted on flying so that Gagarin, who was his backup, wouldn't be sent instead. That's so sweet. During the mission, failures cascaded. One solar panel failed to deploy, leaving the craft with limited power, and control systems malfunctioned. Attempts to fix the problem failed, and after orbiting Earth for a day, Komarov tried to re-enter. The parachute system malfunctioned during descent, and Soyuz 1 slammed into the ground at high speed. Komarov was killed instantly, making him the first person to die on a spaceflight. Radio recordings reportedly captured his final words, cursing the engineers and officials who would let the mission fly. Soyuz 1's failure was a huge blow to the Soviet program. It forced major redesigns of the spacecraft before future missions, but Komarov's death has lingered as an example of how political ambition can override engineering safety. Gay astronauts. NASA has never officially disclosed the sexual orientation of astronauts, but there is historical context. Sally Ride, the first American woman in space, was revealed after her death in 2012 to have had a long-time female partner, making her the first known LGBTQ+ astronaut. Others have spoken about NASA's historically conservative culture and how astronauts astronauts may have felt pressured to remain closeted during the Cold War and early space program years. While no astronaut has publicly come out during active service, there's little doubt that gay astronauts have flown. The lack of acknowledgement says more about the culture of the time than the reality. In recent times, with more inclusivity in STEM and space organizations, it's an open topic that reflects how the astronaut corps has changed since the 60s, thank God. Quasars. Quasars were first identified in the 1960s as mysterious star-like radio sources, quasi-stellar objects. When their spectra were analyzed, astronomers realized the light was highly redshifted, meaning they were incredibly far away. Despite that distance, they were brighter than entire galaxies, making them some of the most energetic objects in the universe. The mystery was solved when quasars were linked to supermassive black holes at galactic centers. As gas and matter fall into the black hole's accretion disk, they heat up and release enormous amounts of radiation across the electromagnetic spectrum, outshining everything else around them. Some quasars also produce powerful jets stretching thousands of light years. Quasars peaked in number billions of years ago when galaxies were younger and had more material feeding their central black holes. Today they're rarer, but they serve as cosmic lighthouses, visible from the edge of the observable universe. Their study has helped map the large-scale structure of the universe and understand how galaxies evolve. A quasar isn't a single type of object, but rather an extreme phase in a galaxy's life cycle, driven by the growth of its black hole. Carrington event. In September 1859, Richard Carrington observed a massive solar flare, followed by the strongest geomagnetic storm ever recorded on Earth. Telegraph systems around the world failed. Operators reported sparks flying from equipment, some even caught fire, and in some cases messages were still transmitted with batteries disconnected because of induced currents. Auroras lit up the skies as far south as the Caribbean, described as bright enough to read a newspaper by. It was the first clear connection between solar activity and effects on Earth's technology, though back then the electrical infrastructure was limited to telegraphs. If a Carrington-level event happened today, the consequences would be catastrophic. Satellites could be disabled, GPS and communications disrupted, and power grids potentially knocked out for months. Modern studies suggest that extreme solar storms are rare but inevitable. It's not a question of if, but when. Tabby's star. In 2015, astronomer Tabitha Boyajian and her team published data from the Kepler Space Telescope about a star officially called KIC 846282, but now nicknamed Tabby's star. It showed bizarre dimming patterns. Instead of regular dips caused by planets transitioning, its light output would drop by up to 20%, sometimes for days or weeks at a time with no clear cycle. Natural explanations were put forward. Dust clouds, comet swarms, or irregular material around the star could block its light. Later observations suggested that fine dust might explain the long-term fading, since different wavelengths of light were blocked in different amounts, something a solid object wouldn't do. Still, for a while it fueled speculation. Some researchers floated the idea of a Dyson sphere, a hypothetical megastructure built by aliens to capture sunlight. That made headlines worldwide, but further studies have found no supporting evidence for artificial structures. As of now, the leading explanation is complex dust behavior, but the exact cause of its strange dimming isn't fully settled. Tabby's star remains one of the weirdest stars ever recorded. Saturn's rings will disappear. Saturn's rings look timeless, but they're actually temporary on cosmic scales. Data from the Cassini mission showed that the rings are slowly, raining down onto the planet, pulled in by Saturn's gravity and magnetic field. This process, called ring rain, is removing tons of material every second. At the current rate, Saturn's rings could vanish in about 100 million years. That's a blink in planetary history, suggesting that we're living at a lucky moment in time. Future observers elsewhere in the galaxy may only ever know Saturn as a plain gas giant. Solar eclipses are a coincidence. Total solar eclipses happen because the moon and the sun appear almost exactly the same size in our sky. The sun is about 400 times larger than the moon, but it's also about 400 times farther away. so the two line up perfectly. This allows the moon to cover the sun completely, creating the dramatic spectacle of a total eclipse. It's a cosmic spectacle, and a cosmic coincidence. Over time, the moon is slowly moving away from Earth at about 3.8 centimeters per year. In the far future, it will no longer appear large enough to cover the sun, meaning total eclipses are unique to our era. Millions of years from now, only partial eclipses will be possible. Gravity is not a force. In Newtonian physics, gravity was treated as a force between masses. The Earth pulls on an apple and the apple pulls back. But Einstein's general relativity reframed the picture. Gravity isn't a force at all, it's the curvature of space-time. Mass and energy bend space-time and objects follow the straightest possible paths within that curvature. What we call gravity is just the effect of moving along those curved paths. A common analogy is a bowling ball on a trampoline. Place a marble nearby and it rolls inward, not because of a force pulling on it, but because the surface itself is warped. In the same way, planets orbit the sun because space-time is bent around it. This model explains phenomena that Newton's theory couldn't, like the precise orbit of Mercury or the bending of light around massive objects. Experiments from solar eclipse observations in 1919 to gravitational wave detections in 2015 have confirmed that gravity is geometry, not a traditional force. Space-time might be 4D. Einstein's theory of relativity treats the universe as four-dimensional space-time, 3 dimensions of space plus 1 of time, combined into a single fabric. Objects don't just move through space, they move through space-time, and gravity is the warping of that geometry. This 4D model is the standard framework physicists use today. The idea can sound confusing because we don't experience time the same way as length or width, but mathematically, treating it as a fourth dimension explains why clocks run differently under gravity or motion, time dilation. Experiments, from satellites in orbit to particles and accelerators, have confirmed these relativistic effects again and again. Some theories even go beyond 4 dimensions, proposing extra hidden spatial dimensions at very small scales, but those remain speculative. What's certain is that space-time itself is 4-dimensional, and that model matches reality better than any alternative we've ever had. Human ashes in the outer solar system. In 1998, a portion of astronomer Eugene Shoemaker's ashes were placed aboard NASA's Lunar Prospector mission, which later crashed into the moon. But the most famous deep space memorial is Clyde Tombaugh, the discoverer of Pluto. When NASA's New Horizons probe launched in 2006, it carried a small vial of his ashes. After flying past Pluto in 2015, the spacecraft is now continuing into the outer solar system, carrying Tombaugh with it. This means human remains have already left Earth's neighborhood, embedded in probes traveling beyond the planets. It's pretty interesting. And that's the end of Layer 4, let's get into Layer 5. Pioneer Anomaly. The Pioneer 10 and 11 spacecraft, launched in the early 1970s, were among the first to travel into the outer solar system. Decades later, scientists noticed something odd. Both craft were slowing down slightly more than expected, as if a tiny force were tugging on them. This unexplained deceleration became known as the Pioneer Anomaly. For years, it sparked speculation. Maybe it was a hint of new physics, or even modifications to gravity at long distances. But in the 2010s, a detailed review of tracking data and thermal models solved the mystery. The spacecraft's own heat, radiating unevenly from their power systems and instruments, was providing a small recoil force acting like a very weak thruster. So the Pioneer Anomaly wasn't evidence of unknown physics after all, but it showed how even small, overlooked effects can confuse deep space navigation when you're working at the edge of precision. Martian waterfall. The so-called Martian waterfall isn't a real waterfall, but an optical illusion seen in spacecraft images of Mars. Dark streaks on cliffs or crater walls can resemble flowing water, but they're typically caused by dust avalanches, landslides, or seasonal carbon dioxide frost moving downslope. While Mars does have evidence of past liquid water, no standing waterfalls exist today. Space blindness. Long-duration astronauts have reported vision problems during and after spacecraft, now known as SANS, spaceflight-associated neuroocular syndrome. In microgravity, fluid shifts shifts toward the head, increasing pressure inside the skull. This can flatten the eyeball, swell the optic nerve, and lead to farsightedness or blurred vision. Studies of astronauts on the ISS showed that about half experienced noticeable vision changes, some of which persisted even after returning to Earth. The exact mechanism isn't fully understood, but fluid buildup and changes in cerebrospinal fluid circulation are key suspects. NASA is researching countermeasures like lower body negative pressure suits to draw fluids back down, since vision loss poses a serious risk for future long missions to Mars. STS-7 window damaged. On June 1983, Space Shuttle Challenger flew STS-7 carrying astronaut Sally Ride, the first American woman in space. During the mission, one of the shuttle's windows was struck by a tiny particle, likely a paint fleck or micrometeoroid, which chipped and pitted the glass. The damage didn't compromise safety, but it was a stark reminder of how vulnerable spacecraft are to even the smallest debris. The shuttle windows were made of multiple thick panes, so the impact didn't break through. Still, the incident it shows that we need to be careful. Next up is my favorite entry on the iceberg: penis on the moon. During Apollo 12 in 1969, astronauts Charles Pete Conrad and Alan Bean drew crude sketches, including a penis, on a checklist attached to their lunar spacesuits. It was a light-hearted prank left by backup crew members who had secretly added cartoon drawings to the mission materials. When the astronauts found them on the moon, they just laughed and played along. Hell yeah. W. Dark energy. In the late 1990s, two teams of astronomers studying distant supernovae made a shocking discovery. Instead of slowing down, the expansion of the universe was accelerating. The best explanation is an unknown component of the cosmos called dark energy now, making up roughly 70% of the universe. Its effect is seen in how galaxies move apart faster and faster over time. Unlike dark matter, which has a gravitational pull, dark energy appears to have the opposite effect, a kind of repulsive property tied to the vacuum of space itself. The cosmological constant, first introduced and abandoned by Einstein, has re-emerged as one possible description. Others suggest dark energy could evolve over time or be evidence of something even deeper in the laws of physics. Despite decades of study, dark energy remains a placeholder name for a phenomenon we don't understand. Astronomers see its fingerprints in the cosmic microwave background, galaxy clustering, and supernova distances, but no one knows what it actually is. Its existence means that the ultimate fate of the universe is still an open question. If dark energy stays constant, expansion will continue forever. If it grows stronger, it could lead to a big rip where galaxies, stars, and even atoms are torn apart. Oumuamua spaceship conspiracy. In 2017, astronomers detected a strange object passing through the solar system, the first confirmed interstellar visitor named Oumuamua. It had an elongated shape, tumbled oddly, and accelerated slightly in a way not fully explained by gravity alone. Unlike a comet, it showed no visible tail. The unusual behavior led to speculation. Harvard astronomer Avi Loeb argued in 2018 that it could be artificial, perhaps a probe or light sail from another civilization. This claim made global headlines, but was widely criticized as unlikely. Most researchers lean toward natural explanations like outgassing of unseen ices or a fragment from a disrupted planet. So far, no evidence supports the alien hypothesis. Oumuamua has long since left the solar system, making follow-up observation impossible. It remains mysterious, but the scientific consensus is that it was a natural object, even if its exact nature is still debated. Zuma disappearances. Zuma was the code name for a classified US government payload launched by SpaceX in January 2018. Official details were never released, but after launch, reports surfaced that the satellite had failed to separate from its rocket stage and was lost. Some sources said it had fallen back to Earth, while others suggested it had successfully reached orbit but remained secret. Because of the classified nature, the true fate of Zuma has never been confirmed. It became a subject of speculation in both space and defense communities. Venusian dinosaurs. In the mid-20th century, some fringe claims suggested that Venus, hidden under thick clouds, might harbor jungles and even prehistoric life like dinosaurs. These ideas came from science fiction and early speculation before space probes revealed Venus's true conditions. When Soviet Venera missions landed in the 1970s, they showed a surface hot enough to melt lead, with crushing pressure and a toxic atmosphere, eliminating any chance of dinosaurs. But fine, we can wish, right guys? And that's the end of layer 5, let's get into layer 6. Moons with rings. Rings aren't just for planets, some moons have them too. In 2014, astronomers discovered that the minor planet Chariklo, which orbits between Saturn and Uranus, has 2 narrow rings. Later, hints of a ring-like structure were also detected around Huame, a dwarf planet in the Kuiper Belt. These are the first known cases of non-planetary ring systems. The mechanism here is thought to be similar to the planetary rings, debris from impacts or disrupted material trapped by gravity. So far, no large moons have confirmed rings, but it's possible small moons near gas giants could maintain them for limited timescales. Final parsec problem. When 2 galaxies merge, their central black holes sync toward each other and form a binary. Simulations show that they spiral together quickly until they're within about 1 parsec, then the process seems to stall. And by the way, a parsec is defined as a unit of distance used in astronomy equal to about 3.26 light years. And where it comes from is that it's like the distance at which the mean radius of the Earth's orbit subtends an angle of 1 second of arc. Whatever the fuck that means, but yeah, it's basically 3.25 light years. Anyways, at that point, most nearby stars have already been flung away, and there may not be enough gas or material left to carry away angular momentum. This stalling is the final parsec problem. If black holes really got stuck at that distance, we'd expect far fewer mergers that are actually observed. Gravitational wave detections by LIGO and Virgo show that black holes do coalesce, suggesting nature finds a way to solve the problem. Possible solutions include triaxial galaxy shapes, interactions with gas disks, or the presence of a third black hole kicking the pair closer. It's an open area of research, but the detections confirm that the problem is more of a theoretical gap than a real barrier. Soyuz TMA-11 superstition. When Soyuz TMA-11 launched in October 2007, it carried the first female space tourist, Anousheh Ansari, and returned later with Peggy Whitson and Yuri Melenchenko. During re-entry in April 2008, the capsule experienced a dangerous ballistic descent due to a separation failure, subjecting the crew to high G-forces and landing hundreds of kilometers off target. The accident revived an old Russian superstition, that missions with women aboard were unlucky. Based as fuck. It echoed a cultural bias going back to the early days of spaceflight. Of course, there's no factual basis, duh, but the superstition still, circulated in the Russian press and stuff, because it's based as fuck. I'm kidding. The end of greatness. In cosmology, the end of greatness refers to a scale around 100 to 200 million parsecs. At smaller scales, the universe has structure. Galaxies, clusters, filaments, and voids. But beyond that distance, matter distribution becomes uniform and isotropic. In other words, the cosmic web ends and the universe starts looking smooth. This observation supports the cosmological principle that at the largest scales, the universe is homogeneous. The end of greatness marks the transition from visible structure to statistical uniformity. You might be a Boltzmann brain. The Boltzmann brain is a thought experiment from statistical mechanics and cosmology. If the universe is infinite and lasts long enough, random fluctuations could spontaneously assemble self-aware entities, brains, complete with false memories. In that situation, it's more likely that you are such a fluctuation than a product of normal evolution. Physicists treat it as a paradox. If your theories predict Boltzmann brains outnumber real observers, then something is wrong with the theory. It's interesting. While not taken literally, the idea forces scientists to refine models of entropy in the universe's future. It's pretty cool. CMB is quantum fluctuations. The cosmic microwave background isn't perfectly smooth. It has tiny temperature variations, only 1 part in 100,000. These fluctuations are critical because they seeded the galaxies and clusters we see today. According to inflation theory, they originated as quantum fluctuations, tiny energy differences at microscopic scales, stretched to cosmic sizes during the rapid expansion of the early universe. When inflation ended, these ripples froze into the fabric of space, later amplified by gravity into large-scale structure. The pattern of fluctuations measured by COBE, WMAP, and Planck satellites matches predictions of inflation-driven quantum origins. It's one of the strongest pieces of evidence linking quantum mechanics to the structure of the cosmos. Photons experience no time. In relativity, time slows down down as you approach the speed of light. For a photon, which travels at light speed, the equations imply that no proper time passes in its own frame. From emission to absorption, a photon does not experience duration. That doesn't mean that photons are conscious, but it highlights how relativity breaks our intuition. For us, a photon from the early universe took 13.8 billion years to reach Earth. But in the photon's perspective, if you could call it that, the journey was instantaneous. And that's the end of Layer 6, let's get into Layer 7. Quantum immortality, do not research. Quantum immortality is a thought experiment, not an established scientific idea. It comes from the many worlds interpretation of quantum mechanics, where every possible outcome of a quantum event happens in a separate universe. Applied to life and death situations, the argument goes that there will always be a branch where you survive. So from your own perspective, you never experience death. But obviously, physicists don't treat this as testable science. It's more of a philosophical extension of the many worlds view, raising questions about identity, probability, and observation. But it's fucking terrifying. Holographic universe. The holographic principle suggests that all the information in our 3D universe might actually be encoded on a 2D surface at its boundary. It arose from the black hole physics. In the 1970s, Jacob Birkenstein and Stephen Hawking showed that a black hole's entropy is proportional to the area of its event horizon, not its volume. This hinted that information content scales with surfaces, not spaces. In the 1990s, physicist Juan Maldacena proposed the ADS/CFT correspondence, a mathematical model where a higher dimensional space is equivalent to a lower dimensional system without gravity. This gave concrete support to the holographic idea, though it applies in a specific kind of universe, not exactly like ours. And it's not proven, but it's an interesting idea. Only one electron exists. Physicist John Wheeler once suggested, half seriously, that all electrons in the universe might actually be the same particle zigzagging back and forth through time. This one electron universe idea was based on the observation that all electrons are identical, same mass, same charge, no variation anywhere. The proposal isn't taken as literal physics since it doesn't match what we see in particle interactions, but it was an influential thought experiment. Astronaut Edgar Mitchell believes in UFOs. Edgar Mitchell, Apollo 14 astronaut and sixth man to walk on the moon, became outspoken about UFOs and extraterrestrial life later in life. He gave multiple interviews claiming that government officials had covered up evidence of alien contact and that he had spoken with insiders confirming it. NASA has never supported these claims and no evidence has been produced to verify them. Mitchell's UFO beliefs are part of his personal legacy, distinct from his achievements as an astronaut. So, I don't know, man. Kinda creepy though, right? The solar system is a zoo. In SETI discussions, the zoo hypothesis proposes that extraterrestrial civilizations deliberately avoid contact with the Earth, much like how humans might observe animals in a wildlife preserve without interfering. The solar system as a zoo framing is a variation on this, suggesting aliens could be watching us while staying hidden. It's like one of the philosophical answers to the Fermi paradox. There's no evidence supporting it, but it kind of makes sense. It's scary. Higher dimensions are folded up at the Planck length. In string theory, the universe requires more than 4 dimensions, usually 10 or 11, for the mathematics to work. Since we only see 3 spatial dimensions and 1 time dimension, the others are thought to be compactified, folded up, or at incredibly small scales near the Planck length, which is 10 to negative 35 meters. It's like the smallest length that we can measure. These extra dimensions would be so tiny that we can't directly detect them with current experiments. Their presence could explain why fundamental forces behave the way they do and why particles have the properties they do. Everything is a spime. Spime is a term coined by science fiction author Bruce Sterling in the mid-2000s. It refers to future objects that can be tracked through space and time via digital networks, sensors, and data. A spime isn't just a physical item, it's something that exists as both matter and information, with its entire life cycle logged. When people say everything is a spime, it's more a speculative idea about technology. The concept suggests that as tracking and computation get more advanced, all objects could become spimes, existing simultaneously in physical reality and in a digital layer of metadata. This one, it confused me. I kind of tried to explain it with the script, but I didn't really get it. I'm sorry. The universe might be a fundamental particle. This is a speculative idea sometimes raised in theoretical physics, that the universe itself could be understood as a single particle-like entity in a higher dimensional framework. The idea comes from attempts to unify quantum mechanics and cosmology, where structures at the largest scale sometimes mirror the mathematical properties of subatomic particles. It isn't a formal theory with experimental evidence, just a philosophical or mathematical analogy. But it's an interesting thought, I like this one. The axis of evil. When scientists mapped the cosmic microwave background, or CMB, with satellites like WMAP and Planck, they found odd large-scale patterns. Certain temperature fluctuations aligned along a preferred axis across the sky. This strange alignment was nicknamed the axis of evil because it shouldn't exist if the universe is truly isotropic, or the same in all directions, basically. The effect could be a statistical fluke, or it might reflect unknown systematics in the data. Some researchers have argued it could hint at physics beyond the standard cosmological model, like imprints from early universe processes. But there's no consensus yet. Living stellar objects. This phrase usually refers to speculative ideas that stars could act like living systems, self-organizing, long-lasting structures that metabolize fuel and evolve over time. Some fringe thinkers have compared stars to living beings, since they take in matter, transform it through fusion, and change states over billions of years. There's no scientific evidence that stars are alive in any biological sense. But maybe they are. Maybe they are, we don't know. They act like it. Backwards time travel is possible inside a black hole. General relativity allows for solutions where space-time curves so strongly that closed time-like curves, paths that loop back in time, could exist. Some interpretations of rotating or Kerr black holes suggest that near their singularities, time and space could behave in such a way that backward time travel is mathematically possible. But these are purely theoretical constructs. In reality, inside the event horizon of a black hole, no information can escape to the outside universe. Whatever exotic space-time behavior happens there, it remains unobservable to us. Another universe seen in the CMB. The cosmic microwave background contains tiny irregularities that trace the early universe. Some researchers have proposed that unusual cold spots in the CMB could be evidence of collisions with another universe in a larger multiverse. The most famous case is the CMB cold spot in the constellation Eridanus. Alternative explanations exist. It could be simply a statistical anomaly caused by a large void or a supervoid in the distribution of galaxies along that line of sight. Current data doesn't decisively distinguish between these scenarios. And guys, that's the end of the Space Mysteries Iceberg. I hope you enjoyed. This is another long one. I had a great time recording and researching and all that for this video. I hope you enjoyed. Let me know if you did. Let me know what you want to see next in the comments. And everybody have a great night. Sweet dreams.